we're going to slowly ramp up the complexity of our examples. So we're going to bring together everything that we've done up till now dealing with forces. And I'm going to add a new force in, and that's in terms of tension. So tension is anything from, like, this would be a rope. So you can think of it in terms of anything like hung by a string, by a rope, fishing line, you name it. If it is hanging or being pulled by something that doesn't have them directly attached to each other, then that would be force of tension that we'd be looking at. So first, before I do anything, what I want you to do on your own now is to draw a free body diagram for both of these boxes. And I will tell you that on our Canvas page, I do have practice with free body diagrams, so you can use that, and I have the solutions posted. So I really suggest that you work through those examples. Okay, so draw your free body diagrams, and then the question I want to ask you is, given this information, all we know is that this applied force is 40 newtons, and we're just asked for the tension and the acceleration. So knowing that, what forces do we have, and do you think that this tension is going to be the exact same as that 40 newtons? So pause this, work on those two questions, and then come on back when you're done. Okay, so let's take a look at this. So first of all, what I want to tell you is there's two ways that we can look at this. One is that I'm going to combine this as a system, and the other is then I can treat them as individual systems. So what I would ask you to challenge yourself with right now, and normally I'd have you talk to your neighbors to see if you agree or disagree, is, do you think that these two things are accelerating at the same rate, or are they accelerating at a different rate? Now let's think about that. So I know that I am applying this force that's pulling this 10 kilograms, and this 12 kilograms is being pulled behind here. Now we haven't done friction yet, and this mentions nothing about friction, so don't assume that it exists. If I'm not told that there's friction, then this is a frictionless surface. So I have these two. Now applying this force, what would it mean if this box, say, had a smaller acceleration than this box? So in other words, these things are going to be accelerating in this direction. I have this force going here. What does that tell me then about this one? If it's accelerating at a faster rate, wouldn't it mean that it is like gaining, starting to close the distance between the two boxes? Now, if it's accelerating at a smaller rate, wouldn't that mean eventually this line would break? So if this thing stays with this line taut, then that means these two things are accelerating at exactly the same rate. So what we can do then is combine this, is treat this as then a system of, let's see, 12 plus 10, so 22 kilograms, with an applied force going that way. You might feel like we haven't accomplished much, but let's kind of take a look at what these two free body diagrams are and how this simplifies life for me. So this free body diagram, let's see, I have the force of gravity pointing straight down towards the center of the earth. I'm a flat surface. The force normal is always perpendicular to the surface. It is pointing straight up. Nothing about friction. So then the only other thing I have is this force of tension. Now I can come over here to this box. This would be for the 12 kilogram. For this box then, let's see, I have the force of gravity pointing straight down towards the center of the earth. The force normal pointing straight up, perpendicular from the surface. And I have this force applied. So I have this force applied, that's this 40 newtons, so that's defined for us. And I have this force of tension pulling back this way. So the first question I can ask myself, and it's related to the first one before we combined it into one mass, is this force of tension the same? My inbox, it's always like that. So is this force of tension the same? Now I come back to my acceleration question. If there is no friction, and we're just focusing on this tension force on this rope is what's going to accelerate this box. If they're both accelerating at the same rate, then, sorry, the dinging of my inbox has just totally derailed me. Then we have the same acceleration, then wouldn't this tension and this tension have to be the same? And it's kind of the same thing in terms of the acceleration itself, right? So if the tensions were different, wouldn't that be like the line breaking? So where I'd have one piece acting, going in one direction and one piece going in another. Well, while it's a one connected system, this tension and this tension between these two are exactly the same. Now what you'll see as we progress, I'll add more boxes on here. And like, so as I go down the line, the tensions aren't the same. That'll become a little more obvious once we do this. So if I look at this, I say, okay, so one of the things I can do is a sum of forces. I know the gravity and I know the normal. Well, I'll know that because it's not flying up into the air or plummeting down to the earth. So the sum of my forces in the y is 0 for this one, and the sum of my forces in the y are 0 for this one. And I know that this force here is being acted in the straight line in the x-axis. So I don't have anything changing this force normal. So I can start with that and go, so the sum of my forces in the y, let's see how that gives me, if I define to the right and up as positive, it gives me the force normal minus the force of gravity. And let's call this mass 1 and mass 2. For mass 1, will be 0. And the same for this one. So for mass 2, the same thing. The sum of my forces in the y is the force normal minus the force of gravity. Now this question it doesn't matter on, but I want to emphasize something for you. And that is a habit to get into, is to label these things as their subscripts for however you're labeling your objects or masses. And because it'll get really easy later on to lose track of which is which. So now let's look at our force of tension. So I know then the sum of my forces in the x without any friction is just this tension force accelerating that one box. So I have the force of tension equals, let's see, mass 1. That's mass 1 times acceleration. Sweet. I can come over here then for my second mass and my sum in the x. I have, let's see, the force applied minus the force of tension equals, let's see, mass 2 times acceleration. So we've decided for ourselves that the acceleration is the same and the tension is the same. So one option that we have here is to do a substitution. I can take this force of tension and put it in for that force of tension. So that gives me that a force applied minus mass 1 times acceleration equals mass 2 times acceleration. I know the acceleration is going to be the same. I don't know what it is yet, but I know it's going to be the same. And I know what this force applied is. So I can move this mass 1 times acceleration to the other side. So I'll get that the force applied equals, let's see, mass 2 times acceleration plus mass 1 times acceleration. Now here's the tricky part. If you haven't done much math, it might not be as obvious to you as to what you want to do. And a lot of you will be really tempted right now to start putting numbers in here. And I'm really going to encourage you to leave it in this form for as long as you possibly can, because A, it's going to save you time, and B, it's going to save you steps. Because let's go ahead and do the next one. So then I get, let's see, I'm going to rewrite this, that I have the force applied equals. Now what I'm going to do is these two accelerations are the same. So what I can do is factor that acceleration out. So I have acceleration times mass 2 plus mass 1. This is a number, these are known values, so I can rewrite this that the force applied divided by mass 2 plus mass 1 equals A. So now I can put in my values. I know that mass 2 is, let's see, our force applied is this 40 newtons divided by the sum of my masses. So mass 2 is the one I said was 10 kilograms plus 12 kilograms. And that equals acceleration. Cool. So that one was just kind of doing this thing, is that I look at it and I do my free body diagrams. And for this one, this wasn't such a bad idea or such a bad path. It wasn't that many steps to get us to where we can isolate and get to acceleration. But let's take a look what happens if we just combine this. So turn this over. Let's take a look at our free body diagram. Believe it or not, it's actually sitting on the ground. It's not floating in space. So I have my force of gravity down, my force normal up, perpendicular to the surface, and then my force applied. Now notice I don't have my force of tension in here because I combined them. So this would be what I would call an internal force. So if that is an internal force, then it's this combined mass, and I only have that one applied force. So now I can do this, define what's positive. I can do this, my force in the x, then is my force applied, I've called positive, oh, that's it, equals my mass times acceleration. Well, remember this 22 kilograms, well, that's force applied equals mass 1 plus mass 2 times acceleration. So now in one step, this is just me reminding you where that came from. In one step, I have that the force applied divided by that 22 kilograms equals acceleration. That's an G. Compared to those steps. So one of the handy dandy things that you can do for yourself is ask, think it through for a second. What does it mean if the tension were different? What would the rope have to be doing, right? And if it's not fraying or anything, then this tension has to be the same. It's traveling along the same path, the same line. So that tension has to be the same. So then the next question is, well, what about the accelerations? Well, what would happen to this tension if this acceleration were anything but the same as that? If you can talk yourself through that, you can get yourself through some of these problems that look very complex and actually simplify it down to this nice, neat little two-step thing. Well, we have acceleration. The downside to this is the one thing I don't have is my force of tension, because notice that's an internal force. That didn't appear here, but I have it here. So I have two options. I can look at this and I can say, okay, so I know what this force applied is. I don't know what this is, but I know what the acceleration is. So I can take this equation that I have here and simply solve it for the force of tension. That's option one. Option two is I look at this and I say, well, there's only one force here. Force of tension then is this mass times acceleration. So my preference would be like, oh, I'll go with that one. But know that you're not wrong either way. It's what makes the most sense to you. So I have now my force of tension equals mass 1 times acceleration. And here's when it's important. I said pay attention to those subscripts so you don't lose what you're working on. So I know mass 1 is what that 12 kilograms is. So force of tension is going to equal mass 1 is that 12 kilograms times this acceleration, which I haven't mathematically punched out yet, have I? Let's go ahead and do that. So 40 divided by 22. Oh, come on. There we go. That is not right. It took the tan of it. Why would it do that? It's still doing it. There we go. 1.8. Sometimes you just have to be persistent with your calculators. So when I divided the force applied by the 22 kilograms, I get 1.82 meters per second squared. And that will give me my force of tension. And I'm done. So let's move on to our next example.